Hi everyone, in today's video we are going to be discussing the concept of frames of reference. So you may be asking yourself, what is a frame of reference? Well, I'm going to define it. So a frame of reference is the position from which motion is observed. So it is the position from which motion is observed. Okay, and this is because all motion is relative. And therefore, because all motion is relative, it depends on the frame of reference in which it is measured. All motion is relative. Because of that, it depends on the frame of reference from which it is measured. Okay, so a way to illustrate this is, say we have two cars. I can't really draw well, so these are my two cars here. And here are the wheels. So we have the red car, and we have this blue car, and say they're driving down the road. Let's draw little people in them. Okay, they're driving. Alright, so we have these two cars, and we have the red car here, which is traveling at 60 kilometers an hour. And then we have the blue car here, which is traveling 50 kilometers an hour. Okay, so for the sake of this, say they are traveling this way. And they're driving basically side by side. So they're side by side. Okay, so from car A's frame of reference, which is the red car, car B, which is the blue car, appears to be falling behind at a rate of 10 kilometers an hour. Whereas inside of car B, which is the blue car, basically the driver there thinks that car A is pulling ahead at a rate of 10 kilometers an hour. And this is because of the frame of reference of each car is different, and therefore the motion each driver observes is going to be different according to which car they're in. So from the view, just to go over this again, from the view of the red car, the blue car is falling behind at a rate of 10 kilometers an hour. And then from the perspective of the blue car, which is car B, I should probably put A and B. But it looks like car A is pulling ahead at a rate of 10 kilometers an hour. All right, so now we are going to talk about what is known as an inertial frame of reference. Inertial frames of reference. Okay, so an inertial frame of reference is a frame of reference in which Newton's laws apply. I think by now we're all familiar with the Newtonian physics and Newton's different laws. So I hope you know what I mean when I say Newton's laws. If not, I should have a video coming up soon that go through Newton's different laws. And when I do, I'll link that in the comments down below. But yeah, basically, an inertial frame of reference, whenever you see this, inertial frame of reference, it basically means that this is a frame of reference in which Newton's laws apply. Some people also call this a fixed frame of reference. Fixed frame of reference. Or it's also called a non-accelerating frame of reference. So these are the last 2 points here, are just pretty much synonyms, but you might see that in case, and just know if you do see any of these synonyms, it basically means they're referring to an inertial frame of reference. So the most common inertial frame of reference is probably the Earth, which is considered to be fixed, although it is hurtling through space in an elliptical orbit at a speed of about 30 kilometers per second while rotating on its axis. And we might think, oh, well, it's accelerating. We generally consider the Earth to be a fixed frame because although, yes, it is accelerating, we don't really feel this acceleration when we're standing on the planet. So we consider the Earth to be a fixed frame. So the Earth is a non-inertial frame. Usually if you're solving a problem, unless it's stated otherwise in the problem, we can assume that the Earth is a fixed frame. A vehicle moving at a constant velocity would also be considered an inertial frame of reference, or a bike moving at a constant velocity, anything of that sort. Anything moving at a constant velocity, we consider it an inertial frame of reference because all the forces on that object are balanced. Okay. So now let's move on to non-inertial frames of reference. Non-inertial frames of reference. Okay, so a frame of reference in which Newton's laws do not apply is known as a non-inertial frame of reference. So that's pretty straightforward. It's basically the opposite of an inertial frame of reference, which makes sense because we basically just added a non in front of the word inertial. So usually when we have something with that prefix, it basically means we're not referring to the other thing. So this is the opposite. It is a frame of reference in which Newton's laws do not, I'm going to write that in big capital letters, do not apply. Okay, so basically this is referring to accelerating frames of reference. Okay, so this also refers to objects. Sorry, my apologies. Basically, objects move within an accelerating frame of reference in the absence of any external force. And this force we refer to as the fictitious force. So, objects move within, and I use that little short form, this means within, for those of you who don't know, within an accelerating frame of reference in the absence of any external force. We're going to go through some examples later to show what this looks like, but basically this external force that we this external force that is absent is also sometimes referred to as the fictitious force. And basically what the fictitious force is, I like to denote this as F fict. If I were to write this out. Basically, this fictitious force is often used to explain motion in non-inertial frames of reference, and it occurs in the direction opposite to the acceleration of the non-inertial reference frame. So sometimes you'll see something referred to as the centrifugal force, which is a reaction force to the centripetal force that is used to explain the acceleration, sometimes used in the explanation of centripetal acceleration. So you might hear people talk about the centrifugal force, and that's what they're talking about. This is a fictitious force that is used to explain the motion of objects in non-inertial frames. And it causes fictitious acceleration, I guess, in a sense. I won't really be spending too much time in subsequent videos talking about the fictitious force, but it is good to have some knowledge about what it is. Okay, so let's go through an example here. I'm going to underline this because it looks like one big block of text, and then we're going to move on. Okay. Sorry, just gotta zoom in a bit, move over. Okay, here we go. All right, so say we have this bus, and this is the top of the bus. I'm just gonna draw a rectangle, but let's assume this is a bus here. Okay, and this is the top of it. Or you can picture it as a truck, like a pickup truck or whatever you want to picture, but this is some moving object. And this bus in this one is at rest, or it is moving at a constant velocity. Either or, it doesn't really matter. Moving at a constant velocity. So say we place a ball in the middle of this bus. I don't know, here we go. So what would happen to this ball if it is in the middle of the bus and the bus is at rest or moving at a constant velocity? Well, no force is acting on this ball because all the forces in the bus are balanced, and assuming no person on the bus comes by and kicks this ball or does anything to it, the ball is going to stay where it is. It's going to remain where it is. But say we had another bus that is just like this one, same bus with the ball inside. So here it is, but instead of the bus being at rest or traveling at a constant velocity, this bus is accelerating forward. So I'm just going to draw a little arrow here. It's accelerating that way. This is forward, I guess. So the bus is accelerating forward. Okay, so from the frame of reference of the bus, the ball would appear to accelerate backwards, but from the frame of reference of the road, the ball is stationary. And this is because the bus is a non-inertial reference frame. The bus frame of reference is non-inertial, but the road frame of reference is inertial. So that's why from the frame of reference of the road, the ball doesn't appear to be moving, but from the frame of reference of the bus, the ball is accelerating this way, backwards this way, in this direction, in an opposite direction. So again, that occurs because the non-inertial frame is the bus, and that's why there appears to be this fictitious acceleration backwards. But then from the inertial frame, which is the road, the ball appears to be stationary. And there is no fictitious acceleration. No force is really being exerted on this ball, again, unless someone were to come by and touch it, but we're assuming that doesn't happen. So if no force is being exerted backwards on the ball, its acceleration backwards is fictitious. And again, it's only caused because the frame of reference of the bus is non-inertial. Okay, the same thing would happen if the bus were to accelerate backwards. So say the bus backs up, and we have the bus backs up, so it's accelerating this way now. Oh, we'll write that in black, sorry. So the bus is accelerating this way. Well, we have our ball here, and what do we think is going to happen? It's going to appear to accelerate this way. It's going to appear to accelerate forward. But we know that this is, again, fictitious acceleration because no force is really being exerted on this ball. It's not being exerted so the ball moves. There's no force being exerted so the ball moves forwards. This acceleration that is caused is fictitious because the bus is a non-inertial reference frame. And again, if we were to step outside the bus and stand on the road and look in through the window of the bus, we would notice that the ball doesn't move because our reference frame of the road is inertial. It's a fixed reference frame, and this is because, like I said, we usually use the Earth reference frame to be considered to be fixed, so that's why we wouldn't see the ball move. Same thing would happen if the bus were to turn. So say the bus takes a sharp turn, and the bus turns this way, it turns to the right. Well, the ball would appear to accelerate to the left. Again, this is fictitious acceleration because no force is really being exerted this way on the ball. But because the bus is non-inertial reference frame, it's going to appear from the frame of reference of the bus as though the ball is accelerating in the opposite direction. Okay, and this would also happen if the bus turned the other way, the bus turns to the left per se, then again the ball would appear to be accelerating to the right. Okay, so now that we are finished with that, okay, so now we're going to move on to a mathematical kind of practice problem. And in this practice problem, a man driving a car accelerates from rest. And when he accelerates, the object hanging from his rearview mirror makes a angle of 12 degrees from the vertical. Say the object is like those fuzzy dice that some people put in their rearview mirror. It makes an angle of 12 degrees with the vertical. And as long as the car accelerates, it will continue to have this value of 12 degrees from the vertical. So as long as the car accelerates, the dice will stay 12 degrees from the vertical. Oops, that's not how you spell vertical. Sorry, vertical. Okay, so what we want to do now is we want to find the acceleration of the car. We want to find the acceleration of the car that is causing the dice to stay 12 degrees from the vertical. Because the car is accelerating, for argument's sake, in this direction. And therefore, this is the acceleration of the car, and therefore the dice have fictitious acceleration in this direction, right? So what we want to do is we want to draw a free body diagram of the dice first, so that'll be our step one. So we're going to draw a free body diagram. So here we have the dice represented as this point. The dice has force of gravity acting on it, and it also has this force of tension in the string. Here, I'm going to label this FG, and this is FT for force of tension. And then it makes a 12-degree angle with the vertical. So now we're going to want to write an expression that represents the sum of these forces. So we know that the sum of all forces in the x direction is equal to the force of tension in the x direction. So the mass times acceleration is in the x direction is equal to, which is the direction the car is traveling in, is equal to the force of tension in the x direction, which is the force of tension multiplied by the sine of the angle, which is 12 degrees. And then for the sum of the forces in the y direction, since the dice is not accelerating in the y direction, those forces are just balanced. So sum of the forces in the y direction is 0. And we can also say that that is the force of gravity is balanced by the force of tension in the y direction. So we can say mg instead of the force of gravity, because the force of gravity, Fg is equal to mg, is equal to the force of tension multiplied by the cosine of the angle. And then if we want to rearrange for the force of tension, we can say the force of tension is equal to mg divided by cosine of the angle. And now we want to take like what we've solved in terms of the force of tension, and we want to plug this in here. Oh, that should have been in red. My apologies. We want to sub this in here for ft. So when we do that, we get that ma is equal to mg divided by cos theta times sine theta. We know that sine theta divided by cos theta is equal to tan theta, so this is mg tan theta equal to ma. We can also cancel out these m's here. So then now we have a is equal to g tan theta, which is what we're solving for. We want to know what a is, what we are solving for. So this is good. So now we know that g is equal to 9.8 meters per second square, or some people will say 9.81 or whatever. I'm just going to say 9.8 here. And then tan of 12 degrees. So if we put this into our calculators, we will get about 2.1 meters per second squared. And that is the acceleration of the car. Okay, so that concludes this video. If you have any questions, please let me know down below. I'm happy to help. If not, thank you for watching, and I'll see you in the next video. Bye.